Hello, students, and welcome to today's lecture, which is going to be our first kind of mini lecture on thermodynamics. You'll have to excuse me because I'm using like the review worksheet that we have for the review one for for ACE. However, the review one is a good basic idea of what we're trying to look for when we go over endothermic and exothermic graphs. And because I'm lazy, we want to go ahead and talk about, essentially the same topics as before. Okay? So, what we're going to be talking about here is kind of the basics of what thermodynamics or thermochemistry is about. Okay? And the first thing is that we're going to have a special term that we're going to use. It's going to be called enthalpy. Okay? And enthalpy is going to be the measurement that we're going to use that helps us to calculate the internal heat or the energy change of a system. All right? So you guys know that when you eat like a piece of fruit or you eat some candy or you eat some Cocoa Puffs or whatever, that has some internal energy in it. And when we measure energy in thermodynamics, the change in energy is going to be measured in enthalpy. Okay? And there are a couple of things that we're going to want to keep in mind in terms of enthalpy and all that as we move through it. And that's going to be the system. Okay? And the system is going to be whatever reaction vessels is being measured or monitored. Okay? So that's usually your experiment. Okay? Then we're going to have the surroundings. Okay? And that's going to be everything else. All right? So everything else is considered part of the surroundings. And then the universe is going to be the last thing. Okay? And that's going to be both systems and surroundings. And the idea here is that when we have a reaction that's going on, it's going to go on in our system. And it's either going to gain heat or release heat into the surroundings, okay? Or it's going to gain energy or release energy into the surroundings. The last term, universe, is going to be kind of like our 0 point, that the energy lost from the system that goes into the surroundings will end up equaling that when we add those two numbers together, the energy lost by the system and that gained by the surroundings is going to end up equaling 0, which for our term is going to be the universe. So the universe energy doesn't change, but the system can go up higher in terms of energy or the surroundings can go lower. Okay? All right. The next thing that we want to go over here is the first law of thermodynamics, okay? And the first law of thermodynamics is essentially just a real quick definition that states that any changes in the energy of a system, okay, that the total energy change of a closed system has to end up being constant, or that you're always going to have some energy go into work and heat, but you're always going to have, that's always going to be the same amount of energy that directly went in. If you think about it, if you're eating a donut, and a typical donut has about 400 calories, well, those 400 calories are going to have to go somewhere. Some of it's going to get turned into fat into your body. Some of it's going to be sugar that goes directly to your brain, that your brain is going to use the energy to think. And then some of it's going to go into, the sugar that's used in locomotion. But all of that energy that was in that donut is going to be converted to either work or heat. Okay? And that's essentially what the first law of thermodynamics is that there's always a balance to, the amount of energy that goes in and the amount of energy that comes out of a system. Okay? Now, in general, when we calculate enthalpy, we're usually going to be concerned about the change in enthalpy. Okay? And usually when we are worried about the change in enthalpy, as chemists, we're not going to concern ourselves with too much work, okay? Work is usually defined as some sort of locomotion or movement that we can use. If you think of an internal combustion engine, the energy that goes into driving the pistons and making the pistons move up and down, that's an example of work. That's something that us as chemists aren't going to be really all too worried about. What instead we're going to worry about is the actual change in heat, because of a lot of our reactions that we're going to work with are only going to have a change in heat. And when we measure that to find our enthalpy, what we're going to do is we're actually going to go ahead and take the enthalpy of our final products minus the enthalpy of our initial products, okay? The last thing that we want to talk about is whether or not a reaction is going to be exothermic or endothermic, okay? So, and then we also want to be able to draw these graphs relatively well. So first and foremost, an exothermic is going to be any reaction where energy is lost in a reaction to the surroundings. Okay? So that means that energy is lost. Energy comes from something and it goes out. Okay? In general, if a reaction feels warm, that means that that reaction is losing its internal energy to you, the person. Okay? So that means that the vessel or the beaker that you're holding on to, that's your system, and it makes you the surroundings, okay? So in terms of the system, it's exothermic because it's giving off energy, and you as the surroundings are absorbing that energy, which is why it feels warm. Likewise, the opposite happens when you have an endothermic reaction. And an endothermic reaction is going to take in energy from you, okay? And that means that it's taking the energy from the surroundings, which in this case is usually going to be yourself, and it's absorbing it into that system, okay? So, if it feels cold, that's usually an endothermic process because it's absorbing energy from you. And if it feels warm, that's usually an exothermic process because it's giving energy off to you. A typical exothermic reaction would be like fire is an example. Fire, it releases that energy and it goes into you. That's exothermic. An endothermic one would be when ice is melting in your hand. That's an example of an endothermic process. It is taking energy from your hand and it's absorbing it into those water molecules. Okay. Next, we want to go ahead and talk about exothermic and endothermic graphs. Okay. So in an exothermic or endothermic reaction, what I want you guys to note is that we're always going to have our, in any of these, what's going to happen is that we're going to have a left side that has potential energy, okay? And this is the internal energy of our system right here. And then at the bottom, we're going to have the progress or time of the reaction. And what I want you to note is that we're always going to have reactants right here. It's going to be relatively high, the reactants. And then they're going to go ahead and go up just a little bit. And it goes up because of activation energy, okay? So nearly every reaction is going to have some sort of activation energy, and that's the energy to get the reaction started, okay? And a exothermic will go to a transition state, and it's going to depend on the one. And then you'll notice that the energy of the products will end up being lower, okay? And the difference between the reactants and the products is going to be our enthalpy, okay, or a change in enthalpy, and that's the difference between these two right here. And that's usually what we are going to be concerned about, is this delta H, okay? So a couple of key points for an exothermic one, that reactants are higher than the products. That should make sense because it has to lose energy. We have the activation energy on the left side, kilojoules, and then we should have time or progress of the reaction. Next is an endothermic one. And an endothermic one, again, it's going to have some of the same essential parts to it, where we have energy, which is going to be measured in kilojoules over here on the left. We're going to have time, but in this case, the reactants start off lower than the products, okay? Which makes sense because we said endothermic is taking in energy. So it takes in energy. They typically have a larger activation energy, which should make sense because the reactants are, pretty low in energy compared to the products. You'll still have that transition state period, and then you're going to have the difference between them, which is going to be the delta H in this case, okay? And so these are the two diagrams that when I talk about an endothermic and exothermic diagram, these are what I want you to be able to draw properly, okay? And in general, when I have you draw them out, what'll happen is that our reactant side of our equation we're going to write here, and then our products will go ahead and write here. And if we use anything to go ahead and help us with the activation energy, so for instance, if we use a catalyst, we'll go ahead and indicate the catalyst right here with the activation energy, okay? That's going to be it for this section on enthalpy and thermochemistry. It's a really basic section. This is one of my favorite types of units simply because it is, thermochemistry. That's fire, heat, energy. And this is what I, as a chemist, understand the world through, is the transfer of energy from one form to another, okay? But for now, we're going to go ahead and close out. And I'm going to want to remind you guys to be lazy. And a brief little reward here. We have a quick little chess puzzle for those that want it. This is using a tactic called intermezzo. And intermezzos are essentially in-between moves. So the move that black did right here was to take the queen. We do this move first before we take the queen because, hey, it's a free piece. And then we take a look and we're like, oh no, our poor knight, it's attacked once, twice. But it can take the queen, and that makes it feel really good. And that's intermezzo, and that's a nice little reward for you guys that actually got to the end of the video. All right. For now, that's going to close us out. Remember, stay lazy.